Okay, it's a pleasure to present Alberto Grünbaum with the talk Signal Processing Miracles and the Korteweg de Vries equation. Go ahead, okay. Alberto.
Well, thank you very much. And with all these Zoom things, I think we are putting to rest the notion that there is no emotion involved in mathematics. It's quite a bit. You never know if you're going to hear this or not. So let me, what I will do is try to explain this rather crazy title. Some of you will look at the title and say, this doesn't belong in this session, and you might be right, who knows. So I added this page here. There are some new results in this talk, and in case I don't get to them, I hope I will, I think I will. They have been posted in the archive recently, and there is a paper that should be online in the journal Inverse Problems already, and the written version may appear sometime next year, okay? So what I want to do really is to explain the title. What am I talking about when I say signal processing, and where does the Korteweg de Vries equation come into this? So the only way that I can try to explain that is to talk a little bit about the way in which I got involved in this at the time when some of you were not even born. I think that applies to some of you. So a long time ago, in the middle of the 70s, there was this piece of technology that developed called CAT scans, and I got interested in that. I coined the word limited angle tomography, and I wrote this paper here, and then with Mark Davison, who was a PhD student with me, we wrote a more complete paper. And in a way, he is responsible for this in some sense, because he got hired by some people in geophysics here at Berkeley to try to image how a crack develops in a rock. So we were not doing medical imaging. They had a very old X-ray machine that could only swing around the rock. In a medical case, it would be swinging around the patient. But for the old machine, it could only swing around this rock about 45 degrees as opposed to 360. So we had a problem where the data not only was very noisy, that's always the case, but it's not complete. And I want to show you how that led me to what some people call nowadays the bispectral problem, and even some of the results, the new ones that will appear today. So if you go to a hospital, as some of us do at a certain age more often, this is a modern CT scanner. And this is essentially the design that was already around in the mid-70s. So if you open it up, something you're not allowed to do, this is the way it looks inside. So there is a gantry, which is the thing that contains the X-ray tube, and this is rotating around the patient, going all the way around, okay? So that's where you get your 360 degrees covering. Now, in our case, we couldn't do that. We only had to go for a certain limited angle, all right? Well, you know the pictures, you have all seen the pictures that appear in this very important application of mathematics, physics actually, math and physics being the same. Now, here I picked up from a rather recent article talking about the case of limited, if you look here, I don't know if my pointer is something that you can see, but assuming that you can, it talks here about the limited angle tomography, and that's exactly the case that I'm interested in, okay? And look at the word band limitation. So these words will appear in a moment. The limited angle and the band limitation are two ingredients that will appear in a moment. So here is the main question that I was interested back in then. Clearly, if you measure, if you take an image all the way around the patient, you should have a better quality in the image. Of course, there is more radiation too. So the question is, what is the nature of this monotonic relation that should exist between the amount of data and the image quality? Does it increase in a concave way, in a convex way? Suppose you measure 5% more, does the quality increase by 1%, by 2%, by 50%? Anyway, so what I wanted to do now is to give you essentially the entire talk in 6 slides. And this applies not only in the case of X-ray tomography. So take any signal processing problem, and you have G is the data and F is the unknown. And assuming that the relation is linear, as it is in the case of X-ray tomography, it's a very good approximation, this is what you have to solve. Just a system of linear equations, but keep in mind that the data is incomplete and very noisy. So you don't have to invent the wheel to do this. Gauss already told us essentially what to do. You should consider the operator E star E. In other words, form the so-called normal equations, okay? Now, the problem here, I'm going to try to make this a little bit, yeah, okay, it's better. So the problem here is that when you form, in any case, and we will see examples, concrete one in a moment, when you form E star E, this is a global operator, and it's given by an integral kernel, or if you're dealing with a discrete version, a huge matrix, I mean 10 million by 10 million. And you need to compute the eigenfunctions efficiently and economically. In practice, this is a very, very difficult thing. And these are, of course, the so-called singular functions of our problem, okay? Now, the main trouble that you have is that this integral operator that you will get will have a small number of truly non-zero eigenvalues. In theory, they are all non-zero, but after the spectral gap, the next positive eigenvalue is about 10 to the minus 12, so, and the spectrum accumulates at 0. The fact that this integral operator has a spectrum that gets very, very lumped together makes this a very, very unstable business when you try to compute eigenfunctions. I mean, it looks like a degenerate subspace, and any algorithm will run into real troubles. Now, if you want to have a reconstruction algorithm that gives you good pictures, you should only aim at finding the projection of the unknown object on the linear span of those singular functions that have the small number. Small may be 1,000, but not 10 million, okay? If you try to reconstruct, do a full reconstruction, all the problems, all the ill-posed nature of the problem will come and bite you, okay? So you have to decide how, you have to compute the eigenvectors that go with the nice eigenvalues, and you have to decide if your image will be well captured as a linear combination of these eigenvectors. If the answer is no, then you have to go further, okay? And measure over a larger range. Instead of 45 degrees, you may have to measure over 60 degrees. But at any rate, doing this is a very ill-posed thing. So here comes the miracle. That's one of the words in my title. I said miracles in signal processing. The miracle is that for the integral operator that I'm going to show you in a moment, you can exhibit a differential operator, very low order, order 2 actually, that has the same eigenfunctions as the global one. Well, that's already a miracle, but there is more to the miracle. Whereas the spectrum of this E star E accumulates at one point, the spectrum of the differential operator is very, very spread out. So numerically, you could not be asking for something better than this. The existence of a commuting thing and the fact that the differential operator in question has a spectrum that is very, very spread out. If it were not very spread out, maybe you haven't really gained anything. And you can ask the question, as I asked myself a long time ago, what is behind the miracle? So I'm happy to report after many, many years that nobody knows, okay? So what do you do when you don't understand what you're trying to do? Well, you look for more examples. Maybe if you have enough examples around, somebody will be smarter than you and say, oh, that's what is actually going on. And what I want to show today is that something that for many of you, these are mysterious words. There is something called the Korteweg de Vries equation. I'm going to write it later. And there is something called the master symmetries of it. But if you look at the things, you find a very, very nice way of extending in other directions some of the examples that go back to David Slepian, way, way back, of the existence of a naturally appearing commuting integral operator and a commuting differential one. Now, this work has been used not only in signal processing, random matrix theory. I'm going to mention a few more things, not too many in a moment. Okay, so here, this is too small for you to see. This is the title of a paper by Tracy and Harold Witham, who unfortunately passed away recently. If you look here, you're going to see this kernel, the so-called sync kernel. This is going to appear in my talk, but there are other extensions. There are the Bessel functions floating around here and so on. Here is one more. Oh, that's not. Yeah, what did I want to do? I wanted to make this smaller and now push. Okay. So let me just say that the hero of my talk is the Korteweg de Vries equation. I want to think of it very much in the spirit that Murad had in the previous talk. For me, the Korteweg de Vries equation is a little bit like the heat equation. It appeared in connection with a very, very specific physics problem, but it penetrated all sort of branches of mathematics, and I don't have time to talk about that. I just want to give you a couple of examples of that. So here is a paper, or a lecture actually, by Ed Witten, written some few years ago. If you look somewhere in the, here it is. The modular space of Riemann surface is governed by the KdV hierarchy of integral equations. Somebody could ask, what on earth does KdV have to do with two-dimensional gravity and intersection theory in model space? Well, it's like asking, why is the Fourier transform such a useful thing? Well, it was introduced to solve the heat equation, but then it goes all over the place. In a similar line, here is a later paper by Kontsevich. And once again, he says the identity is non-trivial, relies on the equivalence of each approach to the KdV equation. So KdV, I claim, is here to stay. And from my point of view, I'm not interested in KdV all by itself. I'm interested in seeing which pieces of math can it be pushed into. So now the talk starts all over again now. We go back a few, pretty soon it's going to be 100 years. So Shannon essentially posed the following problem. You have an unknown signal of finite duration, like my speech today will be long, but it will only last between -t and t. That's what you are trying to find. That's the f in this system of linear equations that I had before. The values, the data, are the values of the Fourier transform, but you only measure that over a certain band. If you remember, the word band limiting appears somewhere. And of course, keep in mind that you only have noisy values of that. Well, some mathematicians that have never played in the real world will say, well, just go ahead and do analytic continuation. You have a function which is of compact support, it should have an analytic Fourier transform. So stop complaining, go and do analytic continuation. Well, you shouldn't even think of that, okay? Shannon knew that perfectly well, and his question was, what is the best use you can do of this information? And he found the answer essentially. You should compute the eigenvectors of this E star E, more or less, and then find the projection of your unknown on the linear span of what I would call the good eigenfunctions. But you first have to compute the eigenfunctions. So here is the statement. I'm replacing the Fourier transform. Well, no, I'm replacing that by the simple capital F. So this is the problem that you have. G is the data. You know that the restriction of the function to a certain interval is the same function because the function has support in the set A. And you know it only, you know its Fourier transform only over a set B. So I'm abusing the notation here. A and B are used as characteristic functions if you want, or as operators. So the system of equations which I had before is written, I'm going to define now E to be this thing BFA. And now we come back to Gauss, you form E star E, you use the fact that the adjoint of the Fourier transform is the inverse, and that's exactly what you have. This is the operator whose eigenfunctions you need to compute. So you chop in frequency space, you take an inverse Fourier transform, you chop in physical space, you take a Fourier transform, and you chop once again in Fourier space. Okay? So this, and when you do this, you get exactly this integral operator here. Okay? The people that actually did more of the mathematical work along the lines that Shannon had more or less talked about were Slepian, Landau, and Pollack in the Bell Labs back in the 60s. This, by the way, is exactly the kernel that appeared in that paper of Craig and Whittam, Craig Tracy and Harold Whittam that I showed you a moment ago. This operator is what I call time and band living operator. And here is the miracle. You can prove with appropriate boundary conditions. You have to be careful. Let me just make sure that I don't mess up too much here. That this operator, this integral one, commutes with this second order differential operator. It has simple spectrum. This is very useful. If you didn't have simple spectrum, the fact that it commutes will not guarantee you anything. Okay? I mean, the identity also commutes with E star E, but it doesn't help you at all. Whereas this guy has simple spectrum and is more than simple. It's very, very, very spread out. Okay? So, well, you may ask, and who cares about any of this? I mean, this is, I want to show you that even if you were doing this in the case of a 6x6 matrix, which I'm going to show you in a moment, computing the eigenvectors of a 6x6 matrix, which is built up to be an honest analog of E star E, can be a very tricky thing, very unreliable. Okay, even if you use LaTeX and the best packages in the world. What I'm going to do is produce an operator, which is a tridiagonal matrix, which commutes with K, and then we're going to find out that whereas computing the eigenvectors of the initial K is horrible, even for a 6x6, doing that by using this miracle is a very, very good thing. Okay, so just a quick numerical example here. This is the matrix of eigenvectors, it says here. The eigenvectors of the tridiagonal thing were, actually these are the eigenvectors of the initial matrix, okay? Now, should you trust this? Well, you're using LaTeX, what could be better than that? QR, what you do now is we compute the eigenvectors of the local object, the tridiagonal matrix, and because they commute and they have simple spectrum, of course, they should be the same eigenvectors, okay? And if you ask QR to do this, you will get this matrix here. So this matrix, if you look carefully, the columns here are very similar, more or less, to the other ones, except for order, okay? Well, if they are really going to be the same, you should be able to compute the matrix of inner product of these two numerically obtained collection of eigenvectors, and it should be the identity up to some permutation and maybe some signs. Well, if you look here, this looks beautiful. This is tiny, tiny errors, and then a 1 here. In the next column, you see 0.999. That's not too bad, okay? Here, well, 0.99 and then some other funny things. But if you start looking here, what should be a 1 is 0.388. What should be a 1 is 0.614, and so on. So this says that the two computations, both of them done with QR, one was partially correct only, whereas the one that you should be using is the other one. Okay, so this is really to illustrate the fact that this phenomenon appears in many other places. Of course, 99.9% of the time, when you have an integral operator, nobody will give you a commuting differential one. But in these cases, there is one. Okay, and that's what you should do in that case. So let me go back to the problem that I was posing before. Okay, so I'm going to describe some old and new results. So the first result, which let me make this a little bit smaller by pressing there, I guess. Yeah. So back in the 60s, Slepian, Landau, and Pollack found a remarkable collection of things. So here is this second order differential operator. Let me say this is not going to be the guy that commutes with an integral one. What this one does is, you recognize this as being the radial part of the Laplacian in Rn, with a minus sign, of course, and its eigenfunctions are going to give you the basis for these expansions that we're going to be doing. So you start with that operator, and well, I just remind you something that everyone knows: the eigenfunctions of this guy are given essentially by Bessel functions. In particular, if I go back for a second, if you took nu to be equal to, say, 1/2, that would be exactly the case of the second derivative. And of course, in that case, these functions will become the ordinary exponentials that go with the Fourier transform. And we are back in the problem of Shannon. Okay? So as I say here, if you set nu to be equal to this value here, then the integral operator that I have been looking at before is put together by putting in here the eigenfunctions of L. And this was the fact that Slepian, Pollack, and Landau had found before. If you were dealing with a different value of nu, instead of putting the exponentials here, you would be putting the Bessel functions. Okay? So here we go. That's what Slepian did. That for arbitrary nu, you take these eigenfunctions, you form the operator with this integral kernel, okay? You let it act in the appropriate space here, okay? So here there is, if you want to call it time limitation and physical space limitation, these two words are interchangeable. It's a matter of choice. What he proved is that in general, this differential operator that is not as simple as the previous one, it has this extra piece here, an operator of order 0, works for every value of nu. Again, if nu is equal to 1/2, this last factor disappears and you're back in the previous case. If you leave aside the A case, which I don't want to talk about today, these are the only examples explicitly known of this phenomenon, where you write a naturally appearing integral operator and you find an explicit commuting differential operator. Okay, that was the situation back in the 60s. So now I'm going to be able to tell you what is the extension that I have found. I've been actually chasing after this for a very, very, very long time. What I wanted to do was to find operators that will be essentially like this Bessel piece, but to which you should be able to add something that for convenience I write like the second derivative of the log of some theta function. And these thetas have to be found somewhere. I will pull them out of some hat later on. This operator will have eigenfunctions, which I denote by this. I mean, this is true. You can put whatever you want here, and this fellow has eigenfunctions. You can then form the integral operator of time and band limiting by doing the same thing that we did before, which what you may not be able to do, and in fact, most of the time you will fail, is to find a differential operator that commutes with the integral one with this kernel. But I will show you cases pulled out of this magic hat where you do find the commuting one. So the differential operators I'm going to be looking at will have this form. Set operators in the variable z. They have order, if you think, look here, the k goes from 0 to 2. So that means the first example is one here of order 4. Notice that I have put these factors in here to be able to make sure that when I do integration by parts, the boundary terms cancel automatically. So I don't have to restrict the domain of the operator. I want the differential operator with a very, very large domain, say bounded functions would be just enough. And this A should be even Laurent polynomials. That's the way that I look for them. And they should have this commuting property. Okay? Now, I will show you that this exists. And the one that, let's see, I will be doing this for several values of I, this I here. So I wrote here at the bottom of the next page, the one that goes with I equal to 2. So they will be written, I mean, this operator here is one that commutes with the integral one, and it's built out of these guys that I call A sub 2 and A sub 0. These were the ones that Slepian had found. Slepian, I hope I have it. Yeah, here. A sub nu is defined to be this thing. It's an amazing fact, which I cannot explain, that the ones that I find are simple polynomials. There is a quadratic piece here in the ones that Slepian had found. Okay? What I haven't told you at all, and hopefully I'll do that sometime soon, is where on earth did I get these theta sub i's that will make all of this work? So let me try to do that. So this is the case for I equal to 3. For I equal to 3, I look for an operator of order 6. If you look carefully here, once again, I put these factors in there to make sure that the domain is as large as possible. I don't want to have to restrict the domain to say functions that vanish with their derivatives to the boundary. And I want to have this property. And once again, the one that I found involves now A1 and A3. Before it involved A0 and A2, and is some very explicit polynomial. So if you were to do the numerical work, which I haven't done, you should take this very explicit operator, okay? And this will have order 6 because all the A's of Slepian had order 2, and start computing the eigenfunctions. I mean, that's something that I'm leaving for young, energetic people. It's an important thing to do, but I haven't done it. I equal to 4, I think you're going to be lucky. This may be the last one that I'm going to display here. For I equal 5, I equal 4, the order is going to be 10. The commuting property is true, and I have the explicit expression for these guys where some coefficients I write explicitly. Well, in the paper, they are given explicitly. Here, I don't want to show them to you, but they are all written in terms of these guys that Slepian had found, A0, A2, A4. You see, there is an alternating property here. When I'm dealing with the even case, in some case you have A0, A2, the next case had A1 and A3, this one has A0, A2, and A4. I am pretty sure there is a very deep reason for this. I cannot tell you what it is because I don't know what it is, okay? It's just an experimental observation. Now, I thought 4 was going to be the last one. I was lying to you. 5 is the last one, that I'm sure. Everything works. Now the order of the operator is 14. Some of you may say, well, this is a crazy thing. You have a differential operator of order 14. Well, we find the differences. We can discretize that to be a sensibly banded matrix, okay? And the eigenvalues should again be very, very spread out. Okay, so let's pause for a moment. I was told that I have 4 hours for this talk. Is that right? I only have 3.5 hours left. Okay.
You're still okay.
There you go. Where did I get the theta sub i's? I kept changing the I, but I never told you who were the theta sub i's. So to explain that, I need to go back to the Korteweg de Vries equation and write it down, okay? So here is the celebrated Korteweg de Vries equation. It comes from water wave theory. Water waves have to do with my problem as much as the heat equation has to do with all of harmonic analysis, for instance. It's just a tool that has permeated all sort of things. So if you have never seen the equation, here it is, okay? It's nonlinear because there is this term here, okay? So there is some dispersion and there is some nonlinearity, and they both go hand in hand in this case. If you never heard of this, it's a remarkable development. This was written by these 2 Dutch guys way back 1880 or something like that. But they have appeared in all sort of other places. I showed you these 2 papers, one by Witten, one by Maxim Kontsevich. This is another one if you want. So this KdV flow, I mean, this by the way, is again, it's a semigroup in the sense that Murad was using before. It's not just a single equation. There is a whole hierarchy of them, of which the first one, the one that is even simpler than this, is this baby. Of course, this is just translations, okay? But there are other ones that can be written where the right-hand side, it will be U sub t, will be some tensor applied to U. If J is equal to 2, I think in this case, you get that one. If J is equal to 1, you have that one, okay? So you take the infinitesimal generator of translations, namely U sub x, and you apply powers of it, of this tensor n, and this tensor n, this must be another Dutch name, Neuenhuis, or something like that. This is a tensor. The tensor that, the thing that you act upon U sub x is, if you want, this is, let me just put the finger back where it should go, is this pseudo-differential operator. You have derivatives here. There is an antiderivative. You have to understand how to set the constant at infinity properly. And one gets the KdV out of this. The KdV equation is just a special case. Oh, come on. There you go. Now I have it. So go back to what I had here. The equation has the form U sub t equal to some mass acting on U. And there are several, there is a hierarchy. The simplest case This is not much of a mess. This is just translation. You don't need any mathematics to solve that. The next one is KDV, and they keep on going, okay? So that is the KDV hierarchy. I have not mentioned, all that I'm trying to do in this talk is explain the title. In the title, I had the word the master symmetries. So that has not appeared yet, but it will. So this is the equation, okay. Before I do that, let me say a few things here. One of the many important things of the KDV flow, and this is true for the whole hierarchy, is that it is what is called the Hamiltonian flow in the appropriate space of functions, okay? But more than that, it is what is called the bi-Hamiltonian flow. I don't really want to expand in this, except to celebrate my Italian friend Franco Magri and congratulate him on the soccer match of yesterday. This was done by Irene Dorfman, Gail van Dijk, and lots of other people here. Being bi-Hamiltonian means the following, that there is not just one way of writing this in a Hamiltonian form. There is more than one. Consequence of that is that there exists another hierarchy of flows. This is what is called the master symmetries. And the way that this is obtained is you apply again powers of that tensor, but not to the generator of translations, but of dilations instead of that. So the master symmetries, as the next slide will show, this is the way it goes. The right-hand side that you put in the equation, the first one, instead of translations, you have the infinitesimal generator of dilations. And this is obtained by putting here the power 0. So you just put dilations. If you put the power j equal to 1, so you apply this tensor to that guy, this is the second one. And the third one. Look at these equations here. These equations, if you forget about the first one, they involve an antiderivative. So you have to be careful when you write this down, okay? So these equations here, I'm showing you, these are the first few of the so-called master symmetries of KDV. What I found, see, I started playing on this game a long time ago. My hope was, if I deform the examples of Slepian, Landau, and Pollack using KDV, I should get something similar. Well, yes and no. Recently, I have a paper with Ignacio Surrian, Milen Yakimov, and Riley Casper, where we show that something happens in that case, but it's not as simple as what happens when you replace KDV by its master symmetries. Don't ask me why, but the more natural, the easier guide to handle is not KDV or KP if you want to be fancy, but its master symmetries, okay? Why is that? I have no idea. I have some guesses and some hints here and there, but that is, that's a mystery. Now, just a little bit of facts that may be natural to some of you or not, I don't know. One of the things that happens when you look at the KDV hierarchy, this is a collection of these infinitesimal generators that Murad was talking about. All of them commute with each other. So if you take the commutator of x1 with x17, so you form the product one way minus the product the other way, you get 0. This is well known, okay? It happens that the master symmetry flows, okay? They satisfy more complicated commutation relations. Among themselves, if you commute two of them, you get this. Sometimes this is These are called the Virasoro relations. Just to mention an Argentinian, congratulations on the soccer of 2 days ago. Okay, so this is L minus J, 0 central charge, and the commutation relations between one hierarchy and the other ones is given in this way. If this fact is really important or not, I don't know. It is one of the things that people know, all right? What people don't know, by the way, let me go back and here show you, no, okay, here we go. If you ask, why don't you write the next one? Well, not only I don't have enough room in the page, as Fermat would say, but I don't know how to do it. Nobody has ever been able to write down in a reliable way the third or the fourth equation in this hierarchy. They are very, very tricky. But what I have found is I have found solutions of them. So I'm getting close to the end. What is the role of the master symmetry of KdV in our problem? Finally, that's what I was supposed to talk about. Remember, I have managed to deform the result of Slepian by being able to add a potential, as long as I pick the potential in that form. And the question is, what are these V sub i's? What do they have to do with the master symmetries of KdV? So that should be the next page. This is what happens. So pick whatever. There are a few here. So for instance, if you take V sub 4, which is one of the good examples for the extension of my initial problem of Shannon, Slepian, Landau, and Pollack, it solves this, call it if you want the heat equation. The parameter is here T sub 3, okay? And on the right-hand side, instead of having, as Murad would have, say, the second derivative of V4, you have this messy guy acting on V4. This is some nonlinear operator here. If you want to go up to V6, I can still write it down. So it happens that evolutions of these flows according not to KdV, but to the master symmetries of KdV, give you examples where this old problem in signal processing can be solved. If you want, here there are some fixed points. I don't think that this matters. Okay. Now, where did I get these theta sub i's? Well, I told you what happens, but where do they come from? You know, let's go back to a paper that I wrote many years ago with my dear friend Hans Toisterman, where we found these two families, I mean, the so-called KdV family and the even family. And the theta functions that I've been using now, the thetas that I had, are written down explicitly in that paper. They were all given in the paper. To be honest, we didn't know that these ones here, which correspond to the even family, were connected with the master symmetries of KdV. What we knew for the KdV family, the thetas happen to be characters of certain representations of GLN, but these ones we had no idea what they were. They solved our problem, but eventually it was Magri and Subelli, I hope I have a reference to them in some place, that identify these guys as being the theta functions for the master symmetries. So yeah, I think this is my last slide, or I'm going to make it my last one. There are many more. There are many, many connections. Don't ask me why they show up. They do show up. I haven't mentioned the word monodromy. I haven't mentioned the word the Darboux process, which is actually extremely important here. Half of the tau functions that appear are, as I said before, representations of some, characters of some representations of GLN. The other half, I don't have a good group theoretical representation. So if there is a group theory person floating around, look at these guys, what is the group, if any, for which they may be the characters? I just don't know. They happen to give the rational solutions of the master symmetries. This was what Magri and Subelli identified after our paper. And all of them are solutions of something called the add condition. So you take the commutator of one operator against another one, you keep doing that, and eventually you kill it. That's what nilpotency means. So I think I've spoken for way too long, and maybe I can stop here. Thank you very much.
Well, thank you, Alberto, for a very nice talk with many topics. Are there any questions? Yes, Diego, please.
Alberto, I'm going to throw something like out of the blue, so don't expect much content into it.